So we've been talking about annuities, and what we've talked about so far is that accumulation phase of the annuity. And in the accumulation phase, in our timeline, we start with a zero balance. And through the time of that annuity, at regular periods, we make payments into the annuity. And at those same regular periods, interest is accumulated and added into the balance of that annuity to get to the end of the timeline where we have some large future value, hopefully. The other side of that is the liquidation phase of the annuity. In this liquidation phase, the opposite's happening. Instead of starting at zero balance and building up to some future value balance, we're starting with a large balance, and we are drawing the money out to get down to a zero balance at the end of the final term. And of course, as always, interest is being paid in at the end of each period. Because we're starting with a large sum of money now and drawing out, we're drawing interest on a large amount that's shrinking down instead of the accumulation phase where we started out drawing interest on nothing and having a building balance. So that formula is going to change slightly. It looks very similar to the formula we had for the accumulation phase, only there is an extra term that is part of it. So we're going to start out looking at if we know the desired monthly draw. We're going to find that required present value. And of course, present value is going to be abbreviated PV. So the PV that is required, present value that is required, is that equal to that regular draw times, now just like in the accumulation formula, there's 3 open parentheses here. Again, I'm going to write this as you would punch it into the calculator, so it's not necessarily in proper mathematical form, but it is in the sequence that you would enter it into your calculator. So it's that draw amount times 3 open parentheses, 1 plus our rate, remember that is the interest rate for 1 year, the percent as a decimal, divided by n, if you recall, is the number of periods in a year. Close our parentheses to the power of n times t. Remember, t is the number of years, the time in years of our term here, minus 1, close parentheses. So far, that looks just like the formula for the accumulation phase. And just like that formula, we're going to divide, open parentheses, r divided by n again. So far the same. Here's where the difference comes, and that's going to be multiplied by, open parentheses, 1 plus r divided by n, close parentheses, to the power of n times t, and then we close 2 close parentheses to end our formula. Let's take a look at some examples of this calculation. Let's say that Sam wishes to draw $2,500 each month for 25 years. If Sam will earn 4.9% interest, what is the required present value? In other words, how much money What is the lump sum of money that has to be in that account at the beginning of the 25 years to be able to draw out $2,500 a month? A note on this interest rate, that's lower than the rates that we were using in our examples for the accumulation phase. And a good reason for that. In most cases, most investment planners will tell you that when you're drawing out, you want to get a little bit more conservative, safer investments that are less likely to lose money. So chances are that rate during this liquidation phase is going to be, on average, at least lower than the rate that you would have during the accumulation phase. So let's go ahead and fill in our formula. So our present value is going to equal our monthly draw of $2,500 times 3 open parentheses, 1 plus 4.9%, so that's 0.049 as a decimal. It is monthly, so divided by 12. Close our parentheses to the power of 12 times 25 years is our t, minus 1, close parentheses, divided by, open parentheses, 0.049 divided by 12, times, open parentheses, 1 plus 0.049 divided by 12, close our parentheses to the power of 12 times 25, and then 2 close parentheses. Let's type this in. So 2,500 times 1, 2, 3 open parentheses. 1 plus 0.049 divided by 12. Close our parentheses to the power of. And in parentheses here, I'm going to put 12 times 25. Close the parentheses and arrow out of that power. Minus 1. Close parentheses divided by open parentheses. 0.049 divided by 12 times open parentheses. 1 plus 0.049 divided by 12. Close parentheses to the power of 12 times 25. Close those parentheses. Arrow out of the exponent and 2 close parentheses. So $431,944.09. So in order to be able to draw $2,500 a month for 25 years, Sam's going to need a balance of $431,944.09 at the beginning of that period in order to draw out the $2,500 for 25 years, every month for 25 years at 4.9%. Let's look at another example. Tim wishes to retire at 62 years of age. Tim would like to draw $36,000 each year until age 89. Find the required present value if Tim earns, let's make this simple. We'll just make a flat 5% interest. So, finding that present value. It's a $36,000 draw times 1, 2, 3. 1 plus, our rate is 0.05 for 5%. N is 1. It's only once a year because it's annually per year. To the power of 1 times, we got to find the years now from 62 to 89. If we subtract that, 89 minus 62 is 27 years. So 1 times 27. Again, the 1 is once a year because we're drawing out per year. 27 years is how long they're going to do it for. Then minus 1, close parentheses, divided by, open up parentheses, 0.05, divided by 1 again, because it's only once a year, times, open parentheses, 1 plus 0.05 divided by 1, close our parentheses, 1 times 27, and then 2 close parentheses. So let's punch this one in, see what we come up with. 36,000 times 1, 2, 3, open parentheses, 1 plus 0.05 divided by 1. Now, realistically, you don't have to put in the divided by 1. It's not going to change anything. To the power of, again, 1 times 27. Similarly, there you don't need to put in the 1 times 27. You know it's just 27. Minus 1, close parentheses, divided by, open parentheses, 0.05 divided by 1 times, parentheses, 1 plus 0.05 divided by 1, close, power of 1 times 27 again, close, and then 2 close parentheses. 527,149.21. So $527,149.21 is the required present value balance there. Now, the other side of the accumulation phase is, what if we know what the monthly desired draw is, and we need to figure out, or we know what we have for a present value, and we know the length of time, and we need to figure out how much we can actually afford to draw out each month. So let's say that we have, let's go back to Sam here, and in this case now Sam has $600,000 saved for retirement. If Sam earns 5.2% interest, how much can be drawn out each year for 20 years? So the formula changes now. We're instead of knowing what the payment is and figuring out the required future present value, we have the present value, and we're trying to figure out what the allowable payment would be. We're working backwards. So what that's going to require us to do is to divide the formula by this whole term. So that payment is going to be the present value divided by that big term. So here our payment is what we're trying to find. I'm going to write it down as our regular draw, our periodic draw, is going to equal our present value, which is $600,000. Instead of times, though, it's divided by that term. 3 open parentheses. 1 plus, our rate is 5.2%, so 0.052. Divided by, drawn out each year, so this is once a year, so n is 1. To the power of 20 years, so 1 times 20, minus 1, close our parentheses, divided by, open parentheses, 0.052, divided by 1 again, times, open parentheses, 1 plus 0.052, divided by 1, close parentheses to the power of 1 times 20, close and close. Let's calculate this out. So 600,000 divided by 1, 2, 3, 1 plus 0.052 divided by 1, close, to the power of 1 times 20, close, arrow out of my exponent, minus 1, close, divided by, open parentheses, 0.052 divided by 1 times, open parentheses, 1 plus 0.052 divided by 1, close parentheses, to the power of 1 times 20, close, arrow out, close, and close. And we hit enter. That ends up being $48,965.37 a year. So if Sam has $600,000 at the beginning of his retirement and can get 5.2% interest, each year for 20 years, Sam can draw out $48,965.37. One more example. Alex plans to retire at age 64 with $1.2 million saved up. See, let's go 4% interest. How much can Alex draw each month until age, let's go 92. So first thing we should probably do is find out how many years that is. 92 minus 64 is 28 years. So now we do our formula here. The payment, that regular draw, in this case it's going to be monthly, is going to equal to our present value, 1.2 million, divided by 3 open parentheses, 1 plus 4%, so 0.04, divided by 12, because it's going to be monthly this time, each month, to the power of 12 times 28 years, minus 1, close parentheses, divided by, open parentheses, 0.04 divided by 12 times, open 1 plus 0.04 divided by 12, close to the power of 12 times 28, and then 2 close parentheses. So 1.2 million, make sure we got the right number of zeros there, we do, divided by 1, 2, 3. These formulas do seem very repetitive, and they kind of are. It's the same terms over and over, but there's a reason for each of them. So we get, on a monthly basis, Alex here can draw out $5,942.55. So with $1.2 million saved, drawing only 4%, earning only 4% interest, for that 28 years, Alex can draw out $5,942.55 a month. So those are the calculations associated with the liquidation phase of the annuity, where you're drawing the money back out and drawing it down to a zero balance.